Hello, and welcome to Factorization Based Word Embeddings in Python, explained for beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this video we are going to talk about a very important concept in natural language processing called word embeddings, and in particular today we are going to see word embeddings obtained using factorization, in particular the singular value decomposition, also known as latent semantic analysis in natural language processing. So in particular in this video we are going to talk about what do we mean by term document matrix, what do we mean by term context matrix, also known as term matrix. We will see the latent semantic analysis, or you can just think of this as a synonym of singular value decomposition in the context of natural language processing. And finally, we will wrap up our video by a hands-on implementation in Python of this word embedding on a simple example. If you are new to our channel, AI Sciences, just a brief introduction of AI Sciences is we are providing a lot of artificial intelligence and data science-based services, including courses, books, consultancies, demand-based software development, and a lot of things. In the description, you can see the links so that you can follow the links and see the nature of services that we are providing at AI platform. And if you are a regular viewer of our channel, then you are very warm welcome to another very fascinating video on the platform of AI Sciences. So let's begin. So first of all, I'll explain what do we mean by term document matrix, because this factorization-based methods, they rely on matrix factorization. So somehow we have to convert a lot of text, or sometimes known as a corpus of data text. We need to convert that to a matrix, and then we will apply factorization on the matrix. But how to convert, how to come up with a matrix? So one such matrix is known as term document matrix, and obtaining this matrix is not very hard, it's very simple. So think about, you have a lot of documents. For example, one document is as you like it, that is one document having a lot of words, obviously a lot of paragraphs, a lot of words, sometimes known as tokens in the context of natural language processing. Think another document as 12th Night, then this Julius Caesar, and Henry V. These are, let's say we have 4 documents, and these are the words, let's say, that are there in these 4 documents. So the word battle appears only once in the document as you like it. The word battle appears nowhere in the document 12th Night. The term battle appears 7 times in this particular document, and the word battle appeared 13 times in the document Henry V. Obviously, this is just a simple example. You can have many more documents, and maybe your vocabulary can have many more words. Actually, the vocabulary in several languages, they range from several thousands, and in certain cases several hundred thousands also. And documents, they also range from millions. You can have several documents from very diverse kind of sources. For example, academic documents, dramas, and chats and posts, newspapers, and whatnot. So that's a term document matrix. And if you see a column vector, this first column vector actually represents, or that's a vector for the document as you like it. If you see the second column vector, which has 4 entries, it represents the second document, which is the 12th Night. So now you can see a document in the text form can be represented very easily and very compactly as a vector of numbers, which is in most of the cases is the requirement of almost all machine learning algorithms to represent your data in terms of numeric form. Also, if you see the rows of this matrix, for example, the first row represents the vector form of the word battle. The second row represents the vector form of the word good, similarly fool and wit. So the rows of this matrix, they represent the vectorized variants of words, and the columns, they represent the vectorized variants of the documents. In natural language processing and in certain other areas as well, these feature vectors or the vectorized representations, these are known as embeddings. So if I just write, you can think of as a vector form is equivalent to call this as embedding. So you can just think of as representing something, or in particular the words or documents in vector form, is known as embedding. It has other meanings as well. Later we will see that you actually represent words or documents, whatever you are focusing on, as points in some higher dimensional spaces. And sometimes there are subspaces in those higher dimensional subspaces in which those vectors can be represented better. So we say that we embed our words in a vector space, and hence the word embedding comes from. Another kind of matrix is called the term context matrix. That is also very common way of representing the counts of different words. Here in term document matrix, we count words as appearances in different documents. Here in term context matrix, we count words based on their contexts. So for example, think a word, hello, how are you, let's say. So I can define, for example, the context of plus minus one window. So for example, in this particular case, if my word is how, then its context is plus minus one words around it. So this is the context of the word how. So I can have a word how here, and in the context I will be having a word hello and a word are. So for example, somewhere here the word hello is the here, and somewhere here I have a word are. So I will see hello appears as a context of the word how, so I will add one here and I will add one here. So if I have a very large body of the corpus, think ideally all the data in a particular language, all the text in a particular language, I can come up with, I can go through the whole text and come up with this term context matrix, where again the row vectors here represents the vectorized variants of, or the vectorized forms of different words. One thing must be noticed that the term document matrix is normally your vocabulary, whatever your vocabulary is, by the total number of documents. Let me call it D, the total number of documents. So that's the size of the term document matrix. However, the term context matrix is your vocabulary times your vocabulary. It turns out that the actual embeddings or the vectorized variants of the words, they can be achieved in smaller subspaces as dense vectors. Particularly in these term context matrices, the representations are really sparse. And in term document matrices, if the number of documents are really large, then you have huge dimensional vectors, whereas lower dimensional subspaces exist in which the words can be represented, even ideally without loss of any information. They can reconstruct it back without a loss of zero, ideally. So it turns out that we can have smaller dimensional representations. By dimension, I mean the number of values in the row vectors. That is the dimension of the word vectors, both in term document matrix and in term context matrix. So one way of getting the dense representations is actually very close to apply the linear dimensionality reduction on that. It is very similar to PCA, principal component analysis, and here it is exactly SVD. So what we really do is think about this matrix as our term document matrix. So think these sentences as documents. Each row, so for example, this particular row represents a word, and the word has total dimensions n. N is the total dimensions. So think n is the total number of documents. Every matrix can be represented as a product of three matrices, where the first matrix is orthogonal matrix, the last matrix is orthogonal matrix, and the middle matrix is generalized diagonal matrix. And that can be done through singular value decomposition. For those who are interested in the details of singular value decomposition, we have a full-fledged series of videos on singular value decomposition, all its implementation and details. So you can see this singular value decomposition lecture series on our channel, the same channel. So what we can do is these values, sometimes known as the singular values in this generalized diagonal matrix, they define the importance, sometimes the variation of the different dimensions in which we are going to embed our vectors. So we can pick or we can choose the best dimensions. For example, ideally, if we do not want to lose any information, we pick all the dimensions that has at least some information, which means the values are non-zero. Or we can discard some of the values having very small information, which means they are very close to zero, and pick just the higher values. So corresponding to the higher values, if we just pick those columns and just drop the columns that are either corresponding to zero values or very small values, then the dimensionality of each word is now very small, depending upon how many non-zero values were there in the singular value decomposition. And this is basically the new representation of our vector, and it's very dense representation. Further, you can also have the document representations as these columns, where here you have discarded certain columns, here you have discarded certain rows, and you can get that. So at the same time, if you have term document matrix, then the rows after truncation of the first matrix U, they correspond to the embeddings of your words. And the columns after truncating the rows correspond to the embeddings of documents. In the case of term context matrix, it is okay to just focus on U because there is no documents there. And we are not going to construct the matrix, the vector representation for the contexts. It's just okay to come up with word vectors. So let's go to Python and see an example and understand how this all works. So I'm loading count vectorizer to build the counts, and I'm loading NumPy for some array processings. So let's load it. Let's say these are several documents. This is document 1, this is document 2, and there are several documents. I've just copy and paste a lot of documents here. And let's say this is our whole corpus, just for understanding. So that's our corpus. What we do is we initialize our count vectorizer and get its transformation. So after that, if you see the vocabulary is and, document, first is, one, second, the, third, this. And if you see this corpus, you get only these words. These are the words. Excuse me. And this is the term document matrix. If you see the very first row, that is the row for the word and. And here it is saying the and appears in the third document, then it appears in this document, then it appears in this document, then it appears in this document just once. Here we can just testify it, that and appears here, and then and appears here, and then and appears here, and then here. That's it. Further, we can see the second row representing the term, the word document. And you can see the document appears in several different documents. The word document appears in several different documents in different frequencies. For example, the term document appears 2 times in document 2. And here we can verify that. It appears here, and then it appears here. So that's a term frequency matrix. Okay, now what? We can have, so the representation here, if you see, is 16 dimensional because we have 16 documents. Think if we have 16 million documents, the dimensionality would have been 16 million. So we can reduce this dimension and make this vector more dense. And I mean, experiments show that actually build a lot of similarities and analogies and a lot of stuff that is very required in natural language processing tasks by just applying the latent semantic analysis using this SVD. So let's apply this SVD here. And here we have this A. It's 9 by 9. Only we pick the 9 because the matrix rank is 9. It picks 9. B is the corresponding values, and C is this. Now, if we just pick the first 9 columns and truncate the total columns were 16, so we have truncated the 7 columns. But still, it is possible that there are certain values in B that are although they are non-zero, but they are very, very small. For example, if we just see B, there are certain values that are very close to 0. For example, this value. And I mean, a lot of values are very close to 0. Only the first 3 values, I think, are the values that are contributing. The rest of the values are 0. In this case, if we just sort the array from the maximum to minimum order, and for example, just pick the first 3 or 4. By the way, there are automatic ways of doing that. Then the W2 is just 3. The new dimensions are just 3 because these are the 3 dimensions that are much more important. The rest of the dimensions can be ignored. And if you see the representation of the word and here now, and that is these three numbers. That's a vector in 3-dimensional space. Similarly, the representation of the word document is the following. And now you can use these representations for any machine learning task, for example, topic modeling and sentiment analysis and machine translation, maybe several other stuff. So that's about word embedding using a singular value decomposition. I must say that it is very close to principal component analysis, and it is very close to dimensionality reduction, the linear form of dimensionality reduction. I hope you have enjoyed this video. If so, please press the like button. Also subscribe our channel for updates, and do share this video with your friends. Hope to see you next time.